Okay, so, right. So I would like to clarify that two things. We talked about divergence. This, for example, is the divergence of a vector field. You know how to take it. You also know how to take the gradient of a function, and you know this. So there are a couple of important properties that you can immediately verify, which you just mentioned, which is that if it's, and this also lends the meaning of what curl is, but it says the divergence of curl is what? 0. And also the curl of a gradient of a function is 0. And at the moment in passing, because at some point you're wondering, well, what has all this got to do with E&M? We're almost at the end of our, all the tools we need, but the list continues for 2-3 more lectures. We need something called the Laplacian. This is a very important object, both for physicists and mathematicians. This is really what allowed people to understand partial differential equations in a systematic way. The Laplacian is of a function, so it's del squared, and you can imagine what that is. It is nothing but the divergence of the gradient. Okay, so well, let's see what that is. So it's the divergence dot df dx. I'm just taking the gradient. Well, now I take the divergence of that. So what I get is a second order partial differential operator. If, for example, if this is equal to something, it becomes an equation. So this is the Laplacian of a function. So in terms of where we are in our toolbox, let me tell you what remains. What remains is, well, we should be able to do more than Cartesian coordinate system. Because if you have a coaxial cable with a cylindrical symmetry, you try to use Cartesian coordinates, you'll be calculating forever. You want to use a cylindrical coordinate system. But what if you have a spherical object? Well, life becomes a whole lot easier when you use the spherical coordinate system. Okay, it becomes very important both in electricity and magnetism and quantum mechanics. This is where orbitals come from. It's the Laplacian in spherical coordinate system. Okay, these are the eigenfunctions of the Laplacian in the spherical coordinate system. All the 1s, 2s, 2b, 2d, all of those orbitals come from this Laplacian written in spherical coordinate system. Why? When you're studying a hydrogen atom, you have a nucleus giving a spherically symmetric potential, right? It's just one proton. Proton doesn't have any direction to it, so either way you look at it, you just see like a spherical object. So you want to use a spherical coordinate system. So that is why we want to use several different coordinate systems. And then the next part, and I hope to do both cylindrical and spherical coordinate system today, and then the remaining of this is the Dirac delta function. That is just a magical experience. So, but it's very handy. The math, if I never told you anything, you'd be totally happy with it. And because we're not mathematicians in this class, if I slide over a proof and if I intuit it, you would never know the difference. But if you're a mathematician, it has to bother you all kinds of crazy. There's a math explanation for it, but that requires a little bit of a subject called functional analysis. And we haven't studied it, and nor do we particularly have to in the business of doing physics. Okay. All right, so let me begin by talking about the cylindrical coordinate system. In the cylindrical coordinate system, we locate points not by x, y, and z coordinates, but we'll use a different set of coordinates. Perhaps, I mean, yeah, portions of it. And you'll see how these things come about. They come about very naturally. So I have a cylinder in mind, so let me draw a sort of a circle. This circle doesn't exist. Okay? Now suppose I have any point I wish to locate in my cylindrical coordinate system. I would use x, y, and z in the Cartesian coordinate system. But in the cylindrical coordinate system, I will use something different. In particular, I will use this distance, the distance from the z-axis, and I'll call that S. I will also use the z-coordinate. Now what I'm going to do is draw my parallel to the x-axis, and you see this azimuthal angle, phi. I will use lowercase phi. If you're wondering what this phi is, certainly you've seen polar coordinates, right? You can drop this guy to the xy plane, it's really, and this is just a projection, the shadow cast by this object. It's this angle is what phi is. So what you need are a couple of things. One is, how are the coordinates related? You can tell that, of course, x, y, and z. Both coordinate systems use z. And so if this distance is s, this is also s, so you can imagine, I'm drawing a parallel to the y-axis. And so this becomes the cosine, this becomes the sine. Remember, this is a 90-degree angle. So just like your polar coordinates, cosine phi, s, sine phi. So from here, you can go back and forth. Given s, phi, and z, you can find out x, y, and z. But we really don't even have to talk about z here, it's exactly the same. Given s and phi, I can find out x and y. And given x and y, maybe we can find out s and phi. Well, can we? In particular, s is nothing but square root of x squared plus y squared. It's the polar distance. Why is that? This is my x, this is 90 degrees, and this is y. So s squared is x squared plus y squared. Yeah? So I get that. Now, phi, it's easy. If I do y over x, see, y over x, I get s sine phi over s cosine phi, and that's just tangent phi. So you can say phi is tangent inverse y over x. You have to be a little careful here. Let me tell you why. And z is z. So the point here is, given s, phi, and z, you can get x, y, and z. Conversely, given x, y, and z, you can find s, phi, and z. With a little caveat that I'm about to describe here. Again, I'm not very good at drawing, so if you have questions, please let me know. Huh? If the 3D picture is not quite clear. Okay, so let me graph tangent. And this is 3 pi over 2. This is sufficient over here for me. Minus pi over 2. You'll get the idea what goes on here. And this is, let's say, the x-axis. And this is y-axis. If you recall, pi over 2 are asymptotes for the tangent function. Tangent pi over 2 is not defined. So if I graph this, it'll look like this. Okay? Even worse, there's a discontinuity over here. So it is this shape. Oh, this is y equals tangent x. So it is this shape that is being repeated. Okay? So this is called the principal domain for the tangent function. So when you take the inverse function, what do? You just lie it down, right? So what will this look like? These are the asymptotes, and you can see where this graph comes in. So what I'm going to do is graph tangent inverse of x. It's this guy. They asymptotically approach minus pi over 2 and pi over 2. But then the problem is, no matter what value of y and x I use, and you use your calculator to compute tangent inverse of that, it's going to give you an angle between minus pi over 2 and pi over 2. Well, that's not true, because what is the range of phi? Goes all the way around, 0 to 360, 2 pi. Yeah, you will never get anything from 0 to 2 pi. You'll only get minus pi over 2 to pi over 2. So that's like, at best, like 1/2 of the plane. So what do you have to do? You have to be a little careful. So let me, the z-axis does not come into play. Let me draw the xy coordinate system, x, y coordinate system. If you have a point here, okay, and if this is phi, first quadrant, you do tangent y over x, and it's going to give you this angle. No problem. Okay? If you have a point here, here y is positive, x is negative. So tangent is going to give you a negative angle. That negative angle corresponds to this angle. What do you have to do to it? Or rather, add pi over 2 to it. One way I recommend that you do is forget phi, compute this angle just by using positive values. And then take pi and subtract this angle and get that angle. Yeah, that will always work in any coordinate system. If I have a point here, forget plus or minus, just put the absolute value and find this angle. Then the phi that you need is actually that. And we won't use degrees, we'll use radian measure. So I'm not going to take this part in. This is very rudimentary, and yet it can be tricky if you don't, if you haven't used this for a while. So homework, you don't have to submit this. X equals 2, y equals -3, z equals 7. Find S and, well, S, phi, and z. You don't have to find z. Z is 7. But just find S and phi and check with each other just so that you have the correct angle. It's not difficult, but I just want to make sure that I remind you of this problem of this inverse tangent. Yeah? Good. But the story continues. Because remember, we have to find divergence, we have to find curl, we have to find the dl element, we have to find dA and d tau, the volume element. So that also continues. We have to bring it here. I'm going to pretend that there's a point here, part of my xy coordinate system, and over here, there might be an electric field at that point. In the Cartesian coordinates, how would you write this electric field? Well, you'll write it in terms of x component, y component, and z component. And then you'll use x hat, y hat, and z hat. And when you say x hat, y hat, and z hat, you mean, unit vector in the x direction, unit vector in the y direction, and unit vector in the z direction. So when we talk about x hat, y hat, and z hat, it's not really at one point, but we are parallelly moving it to all the points so that at any point, any vector can be written as a combination of x hat, y hat, and z hat. So I'd like to say that x hat, y hat, z hat is not just 3 vectors at a point, but rather a vector field. X hat is a vector field whose value at any point is a unit vector pointing in the x direction. Y hat is a vector field whose value at any point is a unit vector pointing in the y direction. So in this case, we will continue to need 3 different orthonormal vector fields. They just happen to be orthonormal. Okay? Or orthonormal, they're unit vector and they're perpendicular to each other. Okay? We're just thinking these sort of a triad moved everywhere. But we have to use vector fields that are natural to the cylindrical coordinate system. And what are they? So this is the direction. How did I get x hat? Well, I go along one axis and I pick a unit vector. So same thing, I'm going to go along the s direction and pick a unit vector field. Let me do something slightly different so it sticks out. This is my S hat. Z hat is easy. What is Z hat? Well, yeah, it's the same Z hat because phi hat is the tricky one. Phi hat points, it's tangential to this circle, points in the direction of increasing. Again, this is my not so terrible drawing of 3 unit vectors that are perpendicular to each other. Can you see it, everyone?
What did you say about
Phi hat is tangent to that circle that I've drawn because that's how phi increases. Yeah? So let me show you my cylindrical coordinate system. Here's my z-axis. Here's a point. And this is my s coordinate. So s hat points this way. Z hat points that way. Then if I look at this circle, this is how phi changes. So phi points this way. So I still get a 3 perpendicular unit vector. Now remember, this depends on the point. Suppose I pick a different point. Which way is s hat? See that? So s hat, phi hat, and z hat depends on the position. It changes direction in space. Again, that's what we typically mean by a vector field. So, well, what are they? Because I know only x hat, y hat, and z hat so far intuitively. So I'm going to write s hat, phi hat, and z hat. Well, let's go. I'm going to leave a little. This is what I plan to do. Let me leave a little space. So what I'm going to do, because this phi and the whole thing is in the xy plane, I'm going to bring this to this direction, because s hat only has x and y component. It does not have a z component. And if I draw parallel to the x-axis here, this angle is phi. So you can see that the x component is that cosine, like always, plus sine phi y hat. Can you see it? If you don't, let me draw you this sort of a boring diagram. I'm only drawing the xy plane now. X, y, circle, s hat, this is phi, this is my x component, this is my y component. This length is 1. So this is nothing but cosine, and that is sine. Yeah? Melissa, you okay? Good. Here's a tricky one. Which way is phi? It's taking the same thing as s hat and rotating it 90 degrees. Right? So can I write this as cosine of phi plus pi over 2, sine of phi plus pi over 2, y hat? If you don't believe me, all I have done is this is my phi hat. So I'm taking this vector and rotating it by 90 degrees. Right. So this is my s hat, right? This is my s hat. This is my phi hat. It is exactly the same as the s hat vector that has been rotated by an additional phi by an angle of pi over 2. Because they're orthogonal, they're 90 degrees apart. Yeah? You guys write it as a different line, but cosine of phi plus pi over 2 is minus sine phi. This is cosine phi. And z hat equals z hat. Orthonormal These are two words, orthonormal vector basis vector fields. Of the cylindrical coordinate system. They are vector fields because they're defined at every point. And look at that, the direction of S hat and phi hat in space depends on the position, as you can tell by this picture. It's a vector field that rotates along with the azimuthal circle. Kind of powerful stuff, right? Yeah.
When you drew that diagram, but on the three-dimensional one, that line that forms phi is parallel with the x-axis, and then there'd be another one parallel with the y, correct?
Look. So you see the circle here?
Mm-hmm.
This is the xy plane. This is S hat. Now if I take this x hat and in the xy plane, if I rotate it 90 degrees, I get phi hat. That's what I'm doing. Is that the answer?
So that diagram is more clear to me. That lower part of the diagram, when you did the projection on the xy plane, and you drew phi.
Oh, right, no. So in this case, the phi would be this way. This is the angle phi.
Mm-hmm.
This is the phi hat.
Yeah.
Again, it is rotated by 90 degrees. Because here the circle would be.
And that line that you drew to actually like demarc.
This one?
That came from the x-axis.
That is this one?
No.
Oh, this line.
Yeah,
That's parallel to the x-axis. Yeah. I always talk about taking an introductory drawing class. But I don't think I'll survive it. I'm sorry?
I said I think we need a whole class on I get so confused with the
Yeah, it is confusing until you use it over and over again. So you may have confusion tomorrow, but as you look at it now, is it clear?
Mm-hmm.
So here the trick is just to frequently watch it. Well, I'll make life a little more difficult for you. Again, please understand this is my XY plane, okay? Z comes out like this. X, Y, and so then this is my S, and what I'm going to do is rotate this point by a small angle, d phi. And then I'm going to look at this wedge. How much is this length? This is ds. This is what? S d phi. What is the arc length? R d theta, or r theta. You know, if I in a circle, if I go an angle theta, how is theta defined? Well, this distance is r theta. That's how theta is defined. So if I go d phi, it's s d phi. So now let's write the length element, the area element, and the volume element, dl. So that we can do line integral, area integral, and volume integral in Stokes' theorem and divergence theorem, for example. Yeah. So if I go only in the s direction, this is my s hat, all I'm doing is traveling a distance of ds. So I get ds s hat. Z is also a nice Cartesian. It's coming out of the board. So let me write dz z hat. Now, of course, I need a Well, I did that for you. This length is SD phi. Correct? You swap, you go through a small distance d phi, the length you're traveling is SD phi. Because if you go through a bigger circle, you're certainly going to, at the same angle, is going to subtend a larger distance. Yeah? Okay.
The reason why we need to keep everything in like we can't just say we increase d phi because dl is like a length.
DL,
It has to be like
it's a small change in length, and typically you can go in all three directions. Yeah? Very often, we're going to always pick along one coordinate system. Okay, when we do a problem, if it's cylindrical coordinate system, likely I'm going to go around in circles. Okay, so there are three components. Let me pick the area vector. Area vector is a vector whose magnitude is the differential area and the direction is normal. So if I have S hat, what is my normal? It's the phi direction and z direction. Correct?
Right, yeah. There's no
Normal to S, the other two.
Yeah.
So, does that make sense? SD phi from the d phi change and then the dz. Now plus phi hat. Tell me, if you go in the phi hat direction, what is perpendicular to phi hat? S and z. So what will it be?
GC. CS. I'm not sorry, right?
Correct.
Yeah.
And what is this? S and phi, right? S, ds, d phi. I've written in wrong order that the S is just ds, but the d phi is s d phi. With d phi, the s goes with it. You know, it's so easy to intuit so quickly, but I could make a mistake. So let me check. S d phi dz, ds dz, s d phi dz. Yep. Are we good? Does it make sense intuitively? Martin. Yeah, so you can get it and lose it, and I do it too. You have to come back and hit it hard. If it's S hat direction, you pick the two directions perpendicular to it, because the normal vector is always perpendicular to the area. So if I look at S, the other directions are phi and z. So for the phi part, you get S d phi, then you get dz. The only difference is there's no phi here because it's phi hat. It's perpendicular to phi. And the other directions are sort of linear, so to speak. It's ds and dz. Back again, the s d phi will appear, the other two. So the trick is, if this is s, this is phi and z. If this is phi, this is s and z. If this is z, this is s and phi. They're the perpendicular elements.
So could we also like kind of take that logic backwards and say if you're going along the dy dz plane, we need a normal, which would be s hat. Because right now we're going backwards. We're going from s hat to the dy.
We already wrote area vector, line element, and volume element for Cartesian coordinate system. Let's not mess with that. Yeah. Volume is easy, length times breadth times height. There's no direction. So d tau s ds d phi dz. Armed with this, you can do Stokes' theorem, Gauss's theorem in cylindrical coordinate system. I need to show you one example. I won't do it in class. Today I'll post a video. It's already in my the playlist, but I'll link it to Canvas and make it clear. Watch it carefully. Okay. The other thing we can also do is compute now the divergence, the curl, and the Laplacian in cylindrical coordinate system. It's a 15-minute video. I'll post another 15-minute video. These are just calculations. So for example, if you want to know, I don't require you to memorize any of it, and you will calculate this. If you want to calculate the expression for divergence in cylindrical coordinate system, you have to convert every quantity in Cartesian to cylindrical coordinate system. And I patiently do that in a video. Watch that video. Ask me if you have any questions. This is a very important homework. I will add this to your first test grade. Everyone submitted to me separately on Friday. You can talk to me if you have questions on Wednesday. Do not talk to each other. Find curl of A in cylindrical coordinate system. This question absolutely does not make any sense to you now. It'll only make sense to you after you watch the expression for divergence in that video. So it's a short video. Yeah? Okay. So whenever you do this, it'll only have components in cylindrical coordinate system. You must have good questions for me on Wednesday. Meaning, watch that video tonight, work on the problem tomorrow, so I can help you on Wednesday. And then you clean it up. So this is problem 1 of exam 1. Do not talk to each other. Do not Google it. What's the fun of that? Ask me questions when I get done. Okay, good. Again, don't be afraid if this doesn't make any sense to you at this point. If you look at the inside cover of your textbook, you will find the Laplacian, the divergence, and curl in Cartesian, spherical, and cylindrical coordinate system. So the inside cover will have the answer. I didn't say give me the answer. So important point. This is what you'll be graded on. Yeah, you should look up the answer. That'll be your guide to see if you're doing it wrong. Again, I want you to. It's easy to find the problem written out here, there, and everywhere. That's not the point. Right? Do it. Okay.
And these are to be turned in unruled paper, like you said?
Unruled.
Right?
Yeah, unruled paper. Neatly. And put sentences in between.
So neat, biography.
I don't expect the best of handwriting, but I don't think I have good handwriting, but I go through the trouble. I think I'm reasonably neat when I write questions. And that's not natural for me. My natural habitat is a scribble. So what I would like to do is very quickly, I won't go through this in such great detail, write out the details you need for spherical coordinate system. I'm sorry?
There's no z hat in this one.
No, there's no z hat. And the mathematicians use the angles wrongly. Their theta and phi in your calculus book is our phi and theta. And depending on how resourceful you are, or how you can intuit a diagram, you should try to see how these equations come about. So suppose I have any point I wish to use spherical coordinate system. What I use here are r, theta, and phi. R, you guessed it, it's the radial distance. Phi, well, I think you guessed it at this point, because what do? Drop it to the XY plane, and this angle is phi, just like your the cylindrical coordinate system, except this angle is theta. So I should give you a coordinate transformation here. It's no more difficult when you write Laplace's equation or curl or divergence in spherical coordinate system. It's just a hassle. So I hope by the time you do cylindrical, where it's slightly easier because of that z hat, you know in principle how it's done, and then I leave it up to you if you want to crank out some divergence and curl and spherical coordinate system. You can, just to get a feel for it, but I won't require it. I don't want to make an error as I write these things down, so what I'm going to do is, and also I have only 6 minutes, so let me go through it, because to some extent you can take this for granted, but you may have seen this in and let me try to motivate some of these. Look, the z coordinate, if this is theta and this is r, and this is my z coordinate, you can see it is r cosine theta. So here's the thing, this is my z-axis, this is my r, this is my theta. So if I do this is z, that is r cosine theta. So if you're careful, you can come up with the same kind of picture. So this is my r, right? First I'll bring it down to the xy plane. When I bring it down to the xy plane, if this is theta, so this becomes sine theta. So this is why you get the r sine theta. Then if you need the x, once you have the xy value, to get the x component, you just do cosine phi, y component, sine phi. So that's how this comes out. Okay, I've shown it to you once. I've quickly gone through it. Just fight it in your head over and over again till you see it. If not, you can. These are the kind of things you can come to my office and say, "Can you help sort of draw it again?" But if I do it now, you'll forget it just as quickly, and it'll be a whole lecture as well. So here too, I need. But I owe you a picture here. This is r hat. This is my phi hat. This is my theta hat. You see that? I hold the remaining two coordinates the same, and I draw a line for the other curve. So if it's r, I just draw the radial direction, I get r hat. If it's phi hat, I keep r and theta fixed, and I just change phi. So this is like the phi hat from cylindrical coordinate system. Now, to get theta hat, I keep r and phi constant, and I just swing it down this way. So these are like the longitudes of a circle. So it's down the longitude. So if you have the Earth, for example, and these are the longitudes, this is at any point. This is theta hat. Latitude. I don't know. I never said it that way. The latitudes are phi hat, and radially outward is z hat. That makes it a whole lot easier, right? Yeah. And then you stare at it. You'll write lots of triangles and make mistakes, or you don't, and then you realize, whoa, this is it. So immediately you'll recall phi hat is the latitude, so it does not have a z component. Make sure sine theta, cosine phi, sine theta, sine phi, cosine theta, cosine theta, cosine phi, cosine theta, sine the. I wrote it wrong in my notes. Minus sine theta. Sine phi, cosine phi. Please check this against your text. Okay. And now I need to get line element. Well, this is easy. I think this is also easy. Now d phi. Can I use this R or should I be using, should I draw this latitude? And should I use that R? Because it's not this R, right? So this is R, this is theta. So you realize this is sine theta. So yeah? In cylindrical coordinates, it just worked out. That was the S. So literally, I'm just doing S over here. But S is nothing but R sine theta. Yeah? Then you play the exact same thing again. Whenever you have R hat, theta hat, and phi hat, you pick the other two. So if I have dA.
Do we need a differential element in the last?
Oh, yeah.
It's just R.
Yeah, sorry. Thank you. So actually, you guys tell me. This is R, and this is the last thing I'm doing, so please bear with me. This is my R. So what are the two things that I'll need from here?
D R. I mean.
No, the other two.
D R D theta, R sine theta.
Yeah, so I have R squared sine theta, d theta, d phi. Then I have theta hat. What do I have? R sine theta, dr, d phi. Correct? And for my phi hat, what do I have? R dr d theta. R squared sine theta d theta d phi, R sine theta dr d phi, R dr d theta. Yeah? What about my volume element? I multiply length times width times height. I would get R squared sine theta dr d theta d phi. There's a nice picture that'll help you get this. I'll load it up on Canvas. But you know what you're doing. You're picking the other two once you get the line element. Again, this is sufficient to compute divergence and curl and everything else. You'll see from, so in addition to today's class video, I'm just going to upload 2 more short videos. And so you'll have to do an extra little study. Not to worry, you have Monday off.
We're making up for lost time.